Alright, what's up everybody? So again, sorry that we didn't get through all this today in drill. So I'm going to go back and cover some things again, and we'll go ahead and clear these things up. We'll go through making our plots point by point. We will go back through the actual models down here that we didn't get to, as well as some additional interpretations, things like that. So the first thing, when we're reading our data, in this case, I already have gender F and gender N in here, and condition N and condition F. But let's just say that it's not there. We'll say that like gender C is the only value that actually exists. So I want to make sure that we're all clear on how to make that this gender C, the gender character column, how to make that into whatever we want. So again, we're going to use an if-else statement. So if we say if-else bias condition gender C, if that equals F, then output the value -1/2, else output the value 0.5. Check how that runs, and you can see like, yep, that runs right, but it didn't add anything to my data. Like I still have the same 15 variables I have. So you have to remember to come up here, and we're going to add this to bias, and we'll call this gender N2, just because. And now, if we look in our bias data frame, we can see that we have this gender N2. If we instead wanted to make this, if you have a character column and you want to make it a factor, for now, just leave it as the character. When you put it in a model, R automatically makes characters into factors, so you don't have to worry about it. But so this is how you will create a numeric coding scheme for this, or alternatively, if instead of using the -1/2 and 1/2, if you wanted to change this to 0 and 1, and we'll call this gender dummy. And now when we check our bias data frame, you see there's our gender dummy. It is our dummy coded gender, where females are coded as 0, males are coded as 1. Alright, so we'll skip past this $ stuff, because that was mostly just trying to get you to understand like what these $ mean as I start using them. In some specific cases that it's just more convenient. The biggest thing is like this is how we will definitely be using it today. And then also if you want to use it for recoding your variables, then that works as well. Let me go ahead and collapse all these down. So don't need to talk about $ stuff anymore. For the piping, I also think, again, just check out this chapter. It's not very long. It's not very much. It's just, basically a blog post length. Like this entire book is here in this form. So it's really easy. It really helps out a lot. So check that out if you're confused about what this piping is doing. But just as an example of a way that would be useful for you to do this is, let's say that you, whenever you're reporting your statistics, you basically always give at least means and standard deviations of your group. So if we're looking at bias, we'll say week 8 bias by gender, and we want to test that, then whenever we're reporting, what we would want to say is like what our means and standard deviations of those two groups are, as well as whether or not that difference is significant. Now, the reason that you're going to report your means and standard deviations, even if it isn't significant, is because then at least if I go back and look at a published manuscript and all they say is it's not significant, and they don't give me effect sizes despite the lack of significance, I need a way to be able to compute so that if I'm going back and looking at a meta-analysis, because yeah, this one study has this effect, but what if I find 50 studies that all test basically the same thing? Some of them find effects, some of them don't. So if I'm trying to do a meta-analysis, I need to be able to go back and retroactively compute those effect sizes. And so if I want to figure out what my week 8 bias mean and standard deviation by gender, then I'll come in here and I'll say the bias and pipe in. Now, just for your information, when you see this just pop up, it's because I have a keyboard shortcut that I just hit Command P and it puts in my pipes for me. So if you want to look up how to do that, you can do that. But that's why I just hit one button and you see those pop up out of nowhere. So I take my bias data frame and I pipe it into a group by. And I'm gonna group it by gender F so that I have my factor labels. And then I'm going to summarize. And I'm going to say that I want mean equals mean of, what did I say, week 8. And then I also want SD equals SD IAT week 8. And then make sure that I have the appropriate amount. And now you can see it gives me my mean and standard deviation for week 8 IAT scores as a function of females and males. So as I'm reporting this, I would say something to the effect of, we blah blah blah. We tested the difference between men (parentheses) mean equals 0.040. SD equals 0.41, comma, and females, parentheses, mean equals, standard deviation equals, and then whether or not this is a significant effect. How you word it is up to you, and there's some flexibility there, but in general, you always need to report your F, degrees of freedom, and your P value. And I, just as my personal convention, I always also report my 95% confidence intervals, but you definitely always need to report your means and standard deviations as well. So in this one, we would report, F parentheses DF1, DF2, close parentheses equals F value, P equals P value, 95% CI, then brackets, and then you have your lower value, upper limit value. And then that's how you would report your F test. So this is just making stuff up here, but let's just say our degrees of freedom were 1 and 78, and our F value is equals 15.25, P equals 0.03, and 95% CI bracket, whatever the difference is, we'll say 2.01 to 7.3929, whatever, that works. So this is how you would report the significance test, your F test, your P, your 95% CI where applicable, as well as your degrees of freedom here. And then in line, you would say something about like males, parentheses, mean equals 0.40, SD equals 0.40, and females mean equals 0.3536, SD equals 0.41. And so like this is basically the information that will be included in like your conclusion, your summary, your write-up. So like that's just another way that piping can be useful. You know, there are other ways of doing this without using the piping that you could instead do summarize, group by bias, gender, F, and then you want to summarize, and then you could basically have the same information here. And that will give you the same information as this pipe, but this is a little bit harder to read because you have to work from the middle out. So you have to start by saying like, all right, so we're going to take the bias data that's grouped by gender and, you know, do this, 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 and work your way out from the middle, as opposed to working in this nice linear fashion where we say, we take the bias data frame, we group it by gender, and we summarize the mean and standard deviation. So moving on from this piping stuff, I'm satisfied with what we have there. For our coding schemes, I don't think we really need anything. You can avoid using this altogether. I'm just going to delete that out. You know, look at when you import your data from the start again. After you do this, check your structure and see what your things are labeled as. Recode them if you need to, or just, you know, if nothing else, just make sure that you're aware that if you get to a point where something says to, you know, create a coding scheme for some specific variable, because you may not know when you read in the data, you may not know which variables we're actually going to be looking at. So there's no sense in sitting here wasting time, you know, creating coding schemes for all your variables when it's a variable that we're just not, you know, we're not interested in at all. Sorry. But when it comes time to recode things, at least you know how to recode them. If you have any questions about this, let me know. So let's get back into the models that we're looking at. So now we are on to, you know, the main portion of working through this stuff. So we want to test, if we want to test a model against a certain value, or we want to test a specific parameter, a specific intercept, a specific slope, a specific whatever, and we want to test it against that specific value. So in this case, we're looking at our average screen time of our participants compared to 10.2 hours per day. So the way that we covered in drill is to just use LHT, which really and truly is the simplest way, and I would really advocate just for doing this. I really don't see any reason not to. Once you do that, then you can check your coefficient to see what the value is, what the intercept is, because the LHT only tells you that it is significantly different than 10.2. But when you check your coefficient, you see that the actual average is 10.75. 10.76. Now you know that this is significantly higher than 10.2, which is the you know, amount that this other sample from this other study did. So the other two ways of doing this would be to transform your data, and you can do this either inline or by creating a new variable. So first, I'm actually going to show you this third way of creating a new variable, where if I wanted to see, you know, if it was different from 10.2, you know, it's possible to just subtract 10.2 from each value of screen time. So if I do mutate bias, screen time, we'll just call it ST adjusted, equals screen time minus 10.2. So I check that and see that, yep, okay, cool, it created my thing correctly. So let me go ahead and append that onto the data frame. Come back in and add that to bias, and now when we look in our bias data frame, we have, no, we don't, because I can't spell. Bias, let me go ahead and remove that one. So now that I've spelled the data frame correctly, when we come over here, we see that we added this screen time adjusted column. So now if instead of doing this and regressing screen time and testing it against a specific thing, we're just going to change this to screen time adjusted. And then when we look at our model summary, for mod STA, when we transformed the screen time variable by subtracting 10.2, conceptually, if the average was exactly 10.2, after we subtract 10.2 from every single screen time value, our average will now be 0. So now that we have our adjusted thing, that the average of this should be 10.2 if the average, or should be 0 if the average was exactly 10.2. When we regress this on the intercept now, what this estimate is telling us is how much higher or lower than 10.2 is that value. And in this case, it's saying, yep, it's significant, and it's significantly higher by 0.5564. So by transforming the variable, by centering it, not mean centering, but this time we're centering it around like our value that we want to test of 10.2. So that's another way to think of this, is that this is the exact same as mean centering, except for we're not centering it on the mean of the variable. We're centering it on the specific value that we're wanting to test against. And so then when we test it against 0, where 0 is our meaningful value of 10.2, is it significantly different? And here we can see yes, it is by it's 0.5564 points higher. And you can do the same thing as that number 3, but you can also do it as you can do it in line instead of doing it like transforming and creating an unnecessary variable. Up here you can just say screen time minus 10.2, and when you do that, it gives us the exact same thing, and it's going to be the same value because it's doing the exact same thing. It's subtracting 10.2 from each screen time and then testing that mean against 0. But again, like if way number 2 or way number 3 throws you off, seems confusing, whatever, it's perfectly fine to stick with just using the LHT. Just know that if you are testing if something is significantly different from a specific value, that you're only testing one LHT. It's one linear hypothesis test, and you're testing, is the intercept different than 10.2? As opposed to equivalence testing that we'll do down below, where now we are looking at, is it lower than this upper boundary, and is it higher than this bottom boundary? So if we want to look at the dichotomous predictor, IAT weak ache scores as a function of gender, so let me change this to another model that has I'm going to do the factorized version so we can compare the output, the results. So if we run that and we get our model summary, and then we run our model summary down here. Alright, so what we're looking at here is, do week 8 IAT scores vary as a function of gender? So when we have this coded as a factor, the intercept
is the average when everything else in the model is 0. Because gender is a factor, that means one of our groups is coded explicitly as 0, and in this case we know it's females because this tells us that the slope is for gender male right here. It says gender.f equals, or not equals, but gender.fm, and that's because if you look in our bias data frame, the gender.f is just labeled as M and F. In this case, it's not male and female. If it was, then this would say, gender.f male. So this estimate is the predicted week 8 IAT score for females. And then here, this tells us that when it goes from 0 to 1, or when the group changes from females to males, we expect that to go up by 0.04579. Down here, where we have the exact same model, only this time it's using the numerically coded -1/2 and 1/2 coded groups. Now our intercept gives us the grand mean. It does not give us the mean of one group or the other. It gives us the mean of both groups together. So again, take the mean of males, the mean of females, add those together, divide by 2. It is 0.38122. The slope here tells us that the difference between one group and the other group is 0.04579. So you just need to make sure that you are paying attention to which coding scheme you're using and what would be the correct way of interpreting that particular output. Alright, so as far as the plotting, again, I'm going to start this from scratch. And in fact, I'm just going to start the entire thing from scratch because, let's just say that this question says, plot this relationship between, gender and week 8 IAT scores and blah, 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 all the standard disclaimers about publication quality, which means, of course, we want, the means and standard deviation, or, the means and confidence intervals, titles, blah, 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 blah. So we need to make a plot, and how are we going to do that? Well, the first thing that, we know if we're plotting our confidence intervals and our regression lines and things, we obviously have to get our predictions from the model. So if we do predict LM, and we're going to do mod G, I'm going to use my numeric for this graph. And so if I run just that line, it just gives me the predicted values. That's it. So, okay, well, I forgot to add interval equals confidence. Alright, so now that gives me these 3 columns, fit, lower, and upper. So my predicted value, the 95% CI lower boundary and 95% CI upper boundary. Alright, cool. So now I need to add that to my bias data frame so that I have all that information all in one data frame so that when I plot it, it all comes from, one place. So I can C-bind that, which is just column. It's binding columns together, C-bind. And I bind all my bias columns with these 3 columns of predict LM, and when I put them together, I can see that, yep, cool. So here's my bias data frame, and then down here it also added these 3 columns on. So now that I have that, instead of saving those as extra variables that I don't need, I'm just going to add my pipe here and move right along. So now I'm going to pipe that straight into ggplot, and in this case, I am plotting by gender, so I know that I'm going to need, we're going to be doing some geom jitter because we're going to do a dot plot with confidence intervals. So I know that my X I need to be gender in, and my Y I need to be week 8 IAT scores.
So at a minimum, we know that that's what we need so far. I'm going to go ahead and add my theme because I know that that's coming. It's always a thing that I'm always going to add, so why not go ahead and add it? And then let's add geom jitter. Alright, so here's what our plot looks like initially, and like right off the bat you can say like, holy crap, this definitely needs some adjustments. For one thing, the jitter on it is way too wide. I'll come back to that in just a second. First, let me go ahead and adjust my axis here so that I have, you know, more clearly separated groups. So I'm going to scale x continuous, and if I add limit equal -1 and 1, now mind that you have to concatenate this and tell it C parentheses -1 and 1. So that tells it the limits of my scale or of my graph are -1 and 1. So that's like the lower boundary of x and the upper boundary of x. But now I have breaks. These are breaks. Whenever you have a tick mark, something that is on your axis. This currently has breaks by default at -1, half, 0, half, and 1. But I don't need these other points. I don't need 0 labeled. I don't need 1 and -1. I just want half and -half labeled. So I'm going to explicitly add in breaks equals C -1 half, 1 half. Run that line. Cool. So now I have an axis that goes from 1 to -1 to 1, but it's only labeled at 1 half and -1 half. So now let's straighten up this jitter a little bit, and let's turn it down and say that our width equals, let's start with 0.5 and see what that looks like. You can see that's still really freaking wide. What about 0.3? Okay, like we're getting better, but that's still a little bit wider than what I'd really like. Let's try 0.2. Even then, I'll go down a little bit more. What if I make it 0.1? Okay, now we're talking. That's a little bit better. Although, like the dots are kind of small. Let's make them a little bit bigger. Let's change the size to 2 and see what that looks like. All right, so there's 2. What about if we change it to 3? Okay, I like that. Except for, because they're all black, you can't see when they overlap. So you need to adjust your transparency, which is your alpha. So let's adjust alpha and say that alpha equals 0.3. Let's see what that looks like. Oh, cool, that works. So like this right here is a good example that if these dots were much smaller, you might not be able to tell that those two were overlapping if they weren't transparent, because it may just look like one big dot instead of two dots that are just barely not overlapping. But again, because I didn't set a seed each time I run this, it's going to be a little bit different. Because that geom jitter, again, randomly moves your points around to scatter them out so that they don't overlap, but it is random. So unless you have a seed that you set, then it's going to continue to be random. Anyway, moving on. So now we have on our x-axis, but like I don't like this being -1 half and 1 half as the labels for my x-axis. And so I want to add meaningful labels to it. So all I have to do is tell it, add the labels of female and male. Alright, cool. So now that's changed my axis labels. So we're looking better. But like one thing that we're definitely missing, obviously, is our, we want a dot that represents the mean for each group and the confidence interval thereof. So let's start with our confidence interval. That one's a little bit easier. So we're going to put in our geom error bar. And we're going to tell it that our y min equals lower, which again, that's if we look at where our data is coming from. If we run this line up here, we have our I'm sorry, excuse me. We have our fit lower and upper. So this is our lower boundary of our 95% CI, and this is our upper boundary for our 95% CI. So Y min equals lower, Y max equals upper. And let's check what that looks like. So it put in our bars here, except for A, it's laid directly on top of the data, and B, it's ungodly wide. So let's bring that in just a little bit with the width by telling it that our width equals, let's start with 0.3 and see what that, it's still a little bit wider than I like it. Maybe 0.2. That's a little more tolerable. I mean, really could go even a little more narrow. That's all right there. But now it still has this error bar directly on top of our plots instead of having it offset. So if we need to offset it, all we have to do is tell R to offset that by telling it that we want the X value instead of just being what it is by default, which is, gender in. So by default, this is telling it that this error bar and this error bar, its X value is the same as the X value for everything else. So instead, we're going to tell it that we want its X value to equal that same gender in as everything else, but plus 0.3. And now, instead of being negative 1/2 and 1/2 as the value for the X value for where this bar should be, it's negative 1/2 plus 0.3 and 1/2 plus 0.3. Although that's a little bit further out than I'd like. Let me change that to try 0.25 maybe. Okay, I can live with that. So now we have our error bar, and now we just need to get a plot for our points for our means. So we're going to need a geom point, and in this case we need to give it tell it that if we go back and look at our data, what is the mean here? The mean that we're looking to plot is this fit value, where you can see if for one group the mean is 0.0 or 0.40, and for the other the mean is 0.35. But all of this fit value falls on one of two values. But regardless, if we tell it that our y equals fit, x equals, we got to use the same thing as our error bars, so gender in plus 0.25. And so now it gives us our mean points there. Those are a little bit smaller than I like it. So let me size those up just a bit and change that to like 3. Yeah, that works. So good enough for that. And now I just want to add a line that represents the overall mean. So I'll tell it that I want a geom horizontal line, H line. And for AES, my intercept, or y-intercept, equals, and we're going to tell it the mean of bias, what are we using here? IAT week 8. Now, just to be absolutely clear, notice that when you're using H line, you tell it y-intercept equals, not intercept and slope. That would be an AB line. But on an H line, it's horizontal. Your slope is 0, so all you have to do is tell it where do you want that line to cross the axis. So once we add that in, it now puts in a mean. I don't really like the way that's a thick black line. I would rather take this and let's first make that equals gray. Alright, so I like that gray line, and then let's make it a dotted line, just because that's my personal preference. Yeah, so now we have our mean line there. We have our raw data plotted alongside our mean and confidence intervals. And so the last thing that we're really missing
is fixing our labels. So all we have to do is add a labs, which is short for labels, and and let's say that our title is Week 8 IAT scores by gender, and then I'm going to tell it that my X is gender and my Y is Week 8 IAT scores. Alright, so now I've got at least the minimum for having the raw data plotted alongside the means and the confidence intervals. I have the overall mean plotted and I have my labels. So that's kind of the process of how you work through making these plots, or how it might look as you work through making these plots, because you certainly don't just sit down and type all of this out and then expect to run one big plot at the end and poof, all your code works. That's just really not how this works. You do have to piece these things together as you go, and trial and error, and work on getting it all where you want it to be. So we'll also do another thing for our continuous predictor here in just a minute. So I want to let's talk about equivalence testing a little bit more, just because I want it to be absolutely clear here. So if we look at, I'm going to delete all, actually no, I won't delete all that, I'm just going to change these values. The difference in IAT scores, let me be a little more clear here and say Week 8 IAT scores. And then I'm going to cheat just to make an example by saying bias IAT Week 8 regressed on, we'll say gender dot F. So it looks like in reality our slope here is 0.04579. So let's just say that we set our a priori boundaries as like 0.07. I don't know, maybe that'll fall in that boundary, maybe it won't, I don't know. We'll just go with it and we'll say 0.07. So we're going to make this model EQ. And then we want to test is the slope of gender here. If it's within this boundary of plus or minus 0.07, then it's too small to care about. So to do an equivalence test with that, we're going to use LHT, and we're going to tell it mod EQ, just because that happens to be, like, there's nothing special about the name mod EQ, just to be clear. Like, that's just what I happen to name it. You can name it whatever you want, it doesn't matter. But then I need to tell it what I want to test, and in this case I want to test the slope of gender, but I can't just hit gender F, because again, when you look at your coefficient, you see that this is called gender.f capital M. So if I just copy and paste the actual coefficient name, and I want to see, is that equal to 0.07, and then that same line again, but I'm going to add negative, and testing there, and we see that gender F 0.07, that's not significant for either one. What if we change that and we just said like any thing of like 0.15? Not quite. This is the problem with making up examples off the top of your head. 0.2. And that'd be 0.054, maybe?
.053. We'll go with that. So we'll roll with this. And we'll say that like we decided that any difference of plus or minus 0.2 is too small to care about. So now when we make our model and we test that against our boundary of 0.2 and negative 0.2, the first one, like the P is, it says 0.1067, but recall that that's you can divide these by 2 when you're doing 2 tests, when you're doing an equivalence test. So that's actually 0.053, or if you want to be like super technical, and we'll just make it 0.21 instead. Then now it's clearly significantly under that boundary. And when you check the second one, it's significantly under that top boundary right here, and it's significantly over that bottom boundary. So now what we're looking at basically is do these confidence intervals, which again, like this is not like this would be the data, but not necessarily the correct. Sorry, just ignore the last 7 seconds of what I said. The point that I'm trying to make is that when you're doing an equivalence test, what we want to know is, does this fall significantly in this meaningless boundary? In this case, if this is our a priori meaningful boundary, we could say like there is sufficient evidence to say that this is a meaningless effect. The conclusion here, this is a meaningless effect. If you were just testing it against 0 or whatever, all you could conclude is we do not have enough evidence to reject the null hypothesis. So we cannot say that there is not an effect. With equivalence testing, we can say there is not an effect. So the difference between equivalence testing and the other is whether you are rejecting or failing to reject the null hypothesis versus this allows you to accept the null hypothesis and say, we have sufficient evidence that based on how we define a meaningful effect, that we can say with confidence that there is not a meaningful effect. Moving on to the continuous predictor, we briefly covered this in drill, and if we just want to use concern 1, and we'll pretend like it's the overall concern score. When we check that, we have our thing here. Now the difference is if we mean center concern 1, so what I'm doing here is I'm telling it to take each concern 1 score and subtract the mean of all concern 1 scores and store that as a variable called concern. And now I'm going to run this exact same thing. So it's just me. I mean centered this concern 1, and I'm just calling it concern now. So mod xx mean centered. The differences in interpretations for these two models. I'm going to run both of these side by side. And so this is the original model with the raw values in them, and then this one down here is our mean-centered model. So again, the intercept is your prediction when everything else in the model is 0. Here with the raw data, where it's not mean-centered, 0 means the estimate, the predicted IAT week 8 score when the concern score is 0 is 0.577, 578. And then for each 1 point increase in concern, we expect this much change. But your intercept, when it's not mean-centered, means when the concern score equals 0. Because down here it's now mean-centered,
Now our estimate tells us for the average concern score, because that's what 0 means. So we predict that for somebody who has the average amount of concern, that they will have 0.377 will be their week 8 IAT score, and for each point that their concern score goes up beyond the mean, we expect their IAT scores to decrease by 0.27. Sorry, this video is getting really long. I apologize for that. So if you have any more specific questions, feel free to contact me, but I'm going to go ahead and get into this other plot real quick. So we're going to walk through one more plot. So same thing, like I want to plot this thing. You know that we want confidence intervals and we want means, all that good sort of stuff. You know it's coming. You know by this point what we mean when we say produce a publication quality plot, or at least the minimum that we're looking for, which is, you know, a nice pretty theme, not left on, you know, that ugly default gray checkered background, blah, 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 that you're going to make some adjustments to your title and to your axes labels and things like that. But so for now, like, we just want to, you know, plot out this model right here. So like the first thing I need to do is I'm going to need my prediction values and my confidence intervals. So again, I'm going to use predict LM. I'm going to tell it I want to predict mod XX mean centered, and if I run just that, it only gives me the predicted values. It doesn't give me the intervals. So I add interval equals confidence, and so that alone, just that line, will give me my fit, lower, and upper. So just like we did before, like, okay, cool, now I'm going to C-bind that with the bias data frame, and when I look at that, okay, cool, that line runs correctly. It produces my bias data frame with these 3 additional fit, lower, and upper values on there as well. So that makes the data I want. Cool, let's pipe that into ggplot. And this time I'm going to tell it that I want my x to equal concern, which in this case is the mean-centered concern, because that's just concern is the mean-centered variable that I created up here. I don't know. Sorry, I got distracted. My mouse keeps getting really big suddenly, or my cursor. Anyway, so x equals concern, and my y I'm going to say is the IAT week 8 score. And then at a minimum, I know I'm going to add my theme, so I'm going to go ahead and add it. And then I need some points. So let's add in geom point and run it. So here's where we're starting. Cool, got it. A lot of stuff that we need to adjust here. So let's say for starters, we certainly need to add our confidence interval in our regression line. So we'll add our geom ribbon, and we tell it that our y max equals the upper value that we put in there, and our y min equals the lower value that we put in there. And check, see what that looks like. Alright, cool, but like it's got this big black bar. That's because we didn't adjust the alpha. So let's change that alpha. Let's set it to 0.1 and see. It's a little, make it a little bit darker. 0.15. 0.2. That works. So we'll leave it at that. Now, like if you want to have like colored lines around this, then you could tell it like to make the color, you know, purple, and it'll put that purple line around it. If you want it to be just the line and not to have it shade in, then your alpha equals 0, and now you have just the line. But that's not what I want to go for. I'm just going to leave it gray without the colored line, just so that now I have my confidence interval there. Then let's add in our regression line. So we need a geom AB line. And for our aesthetics, now we need, unlike before where we were just putting in a horizontal line where all we need is an intercept, in this one we do need an intercept and a slope. So we tell it the intercept equals, and again, because we're using this model right here, we just tell it to get it the intercept from that model using our coefficients. And our intercept is the first thing in the coefficients. So just to reiterate where that's coming from, if I come down here and I run just this line, it gives me my intercept and my slope for concern. So if I look at just like the first value there, it gives me my intercept. And if I look at just the second value, it gives me my slope. So that's where this right here is coming from. Where this coefficient model xx.mc 1 and 2. So my slope or my intercept is the first thing, and then my slope equals coef mod xxmc, the second thing. So let's throw that in there. Oh, I can't spell. Oh, no, it's just because I didn't have an equals. There we go. So now we have our regression line, and like, I mean, if you want to make that blue or whatever. There it's blue, or I mean, if you wanted to change the line type and make that dashed, like, you can do that. You sit here and you adjust things, you know, one piece at a time, but I don't necessarily want to do that. Alright, cool. So we've got that so far, but I actually don't even want that to be blue. I want to keep that black, but I do want to change these points because I don't really like those how they are. First of all, they're too small. Let me change their size. And the size of these points, let's say 3, see how that looks. Change our alpha, maybe 0.3, let's see. So there's an awful lot of overlap there. And, you know, if that's the case, maybe I will change this, the confidence interval. Instead of filling in the alpha, I'll just add color equals blue. If you ever get some sort of error that tells you that, like, non-finite location or size of viewport, just run the thing again. Normally it'll work. To this day, I don't know what that is. Sometimes if you have, you know, like your window's too small, like if you have it like this and you try to run a plot, it will throw an error because it'll basically is trying to tell you that it can't really plot something that small or whatever. So sometimes you may need to, like, just adjust the size of your window. Sometimes you get an error, and literally, like, I mean, you just saw it. Like, I ran this, I got this error, I immediately ran it again and it worked. You know, that happens. It's just part of technology and stuff. You know, sometimes your computer needs to be reset, and whatever problems it was having, it's no longer having. But that's neither here nor there. You know, I guess the point is that here's your confidence interval and all that sort of stuff. Your regression line. We need some meaningful labels for sure. So we'll add labs, and our title is week 8 IAT scores by concern.
and then our y equals week 8 IAT scores, and then our x equals, and now I'm going to call this one concern score mean centered. Check that, like, alright, cool, now we've got that. And so something kind of like that, you know, that's good enough. We have our, oh wait, no, I guess it would be pretty nice to at least add in, you know, some sort of meaningful line for the horizontal line, and we'll say that our y-intercept equals, maybe you want to put in a 0 line and say, like, here's 0, you know, or maybe you want to put in same thing except for, you know, mean of bias IAT week 8, and for this one we'll say that we want it to be color equals gray and line type equals dotted. Oh. So the reason that just had a problem is because I opened up my aesthetics, and the only aesthetic that I'm using is this one. And so I was missing this parentheses right here to then say, like, no, my color and line type is this and this. And now I have this extra parentheses over here, so if I add that parentheses correctly, like, I can see that, but like, I don't really care for that one. I'm going to take that off, and I'll stick with just 0 for now. Run that plot again, and perfect. There we go. Good enough. Close enough for government work. The one thing that I didn't cover is like this ggSave for exporting your plots. Like, you can just use this export and save as image, you know, save as whatever, blah, blah, blah. You know, you can have these different formats. You can adjust your sizing and things like that. Where you're saving it to, all that sort. So there is this manual way of doing it, but I wanted to point out that there's also ggSave, and that this is a pretty simple, straightforward way of doing it. That, like, by default it will just save your last plot. So if right now if I run ggSave your file name.png, it will take the last plot that I made and save it in my working directory as a PNG image called your file name. If I run this one, it will save it as your file name.tiff. It's a TIFF image file. Or this one will save it as a PDF. If I had a plot called plot2, so you can specify you know, which plots. But for now, this video is long enough, and you'll have enough work to do with your exams. So it's perfectly fine if you just want to come up here and save this as an image, you know, adjust your size to be however, you know, it doesn't really help if it looks like this, but if you have it like this and you click save, this is what your graph will look like. So, you know, make it, you know, a meaningful size, make it pretty, change your file name, you know, save your image, and then click save, and it will save that file, that graph, to your working directory. Anyway, that's long enough for today. Sorry about the length of this, but, you know, I guess it's just part of it. Hopefully this helps you out, and if you have any questions about any of this, just let me know.